This whole chapter we've been talking about functions, doing different things with functions. Today we're going to talk about transforming them in some way or another. And there's a lot of different types of transformations that can take place. You might remember some of these from like geometry when we move things. And even algebra 2, we talk about some of these things where we take a function and we might move it left, right, up, or down. We might make it get a little bit wider. Like if, let's say, it's a parabola, maybe make it get really wide or maybe get really skinny. Sometimes we can make it flip upside down. We can do something to change the shape or the size of the graph. It'll still, like, if it's a parabola, it'll still be a parabola, but it's going to be changed in some shape or form. And so the one thing I'll mention here is all those functions that we talked about in the very first section of chapter 2. We talked about, obviously, quadratic. We talked about linear. We talked about absolute value, cubic. And we had a list of about 6 or 7 functions. We're going to see all those functions today. And all of these transformations can take place with any of those. So when we talk about these rules today of these transformations, these rules work for any function that we have. Doesn't matter what type of function that it is, these rules will be in play for any of them. It might look a little bit different based on the function that I have, but the rule will be in place still. Okay, first one is what we call vertical or horizontal translations. Okay, and that's the name that the book is going to use, right? Sometimes you might have heard of this as like a slide, where we're going to slide the graph left, right, up, or down. But a translation is simply some type of movement. We're going to take the graph that we have and we're going to move it in some fashion. Sometimes it may just be to the right, sometimes it may just be up or down, sometimes it may be a combination of those two. Okay, so there's 2 rules here to talk about. First one is a vertical movement. And so what I'm going to start with is f of x is the original function. So that would be like what we call our parent function, or the function that we start with. For instance, y equals x squared. That'll be one that I come back to a lot because we've done a lot of work with quadratic equations. And so that would be the original function that we want to begin with. But it could be any of those functions. Okay? And there's 2 things that we're going to pay attention to that makes this graph, whatever it is, move up and down, because vertical movement is up and down movement. If we add something to the end, that means it's going to make the graph move up. So if I put a +3 after the function, it's going to move that graph up 3. Okay, if I did it the other way and said, let's take that original function and put a minus at the end, then that's going to move it down b units, whatever that number is. Okay, and so a vertical movement is going to be at the end or after the function. A horizontal function is a little bit tricky, or a horizontal movement, I should say. Once again, we're going to start with f of x being the original function, whatever that original function might be. And when we do this one, this is where it gets a little bit tricky. If I said y equals f of x minus d, when I initially see this and I see this minus sign, horizontal movement means left or right. So when we see minus, we initially think that it's going to be left. But when we do horizontal, this is going to move it to the right. So it's inside of the function, but we're going to move it opposite of what we think. And so I'm going to put that word right here. Whenever we do a horizontal movement, it's going to be opposite of what we would normally think. And then if I put a plus sign in between, or inside the function, it's going to move it left, however many units, whatever that d value would be. Okay, and we can do a single movement, or we can do kind of a combination of the two. And so I'm going to give you a couple of examples before we talk about some of the other ones. Let's say that, let's start with an easy one. We've already kind of seen one like this. Y equals x squared. So y equals x squared would be my original parent function. And then we have a minus 6 at the end. Okay? And so what this is going to do is this is going to move it down 6 because it's after the function. It's after the x squared. It's not connected to it. Here, this is a combination. This has both movements in it. This one is connected to the x because it's inside the function. It's connected to the x. This one's at the end. Okay, so here there's two things that are happening. The plus 3, this is the one that we're talking about. It's going to be the opposite. So plus 3 is going to move this to the left 3, and then the 5 at the end is going to move it up 5. Okay, and one thing that I'll show you here is you can use your calculator to kind of verify what's going on here. So if I were to put this one into my calculator, just to kind of, this would work with any type of equation. If I said that absolute value of x is another one that we've seen off and on, the rules will remain the same, okay? So if I gave you a function that said y equals absolute value of x minus 2 minus 3. Okay, we got two things that we identify. First of all, the minus 2 is on the inside of the function. It's on the inside of the absolute value. The minus 3 is at the end, or after the absolute value. So this is going to move it left or right. This is going to move it up or down. This is the opposite, right? So because it's minus 2, it's going to move it to the right 2. And then the minus 3 is going to move it down 3. So the rules stay the same. The only difference is my original graph is absolute value. So it's going to be a V instead of a U, right? It's just going to be a different kind of graph is all. And I can do that with any of those functions. Another one, and there's some of these that we don't recognize as much, just because we haven't seen them as much. I'll throw this one out there because we don't really see this one very often. But if I were to give you this one. This is what we call the reciprocal function. This isn't one we've spent a lot of time in. But the rules are still the same, okay? This is connected to the x, right? If it's connected to the variable, then this is going to be my left and right. This is at the end or after the function. This is going to go up or down. So in this case, this is going to go left 1. And it's going to go up 5. The rules don't change, right? It's just the type of graph that we have that will change for each one. But trying to recognize and identify what's going on makes it a little bit more difficult because each problem that we're going to see today is going to have a different function that's being used. And so that's the part that sometimes is a little confusing. Okay, and these are all rules I think that we've seen before, right? Algebra 2, we talk about these a lot. And I'm not going to give you examples of every single function because there's like 6 or 7 functions that we can make these changes to. right? And so I'm not going to go through all 7 functions and show you examples because the rules still remain the same. All right, the second type of transformation are reflections. Okay, reflection is taking a point and reflecting. We kind of talked about it yesterday for symmetry, where we reflect that point over a certain x-axis or y-axis or whatever, and it changes the look of the graph a little bit. For yesterday's symmetry, we just talked about reflecting it over, so I ended up right on top of the graph. Because we had that line of symmetry, today it's going to make the graph appear a little different. So once again, if we want to reflect the x-axis, that's probably the most common one. And this is one that we've seen a lot over the years. Once again, f of x is my original function, whatever that function is. I'm not just going to use one function here because it works for all functions that we have. Any of them that we apply this to, it'll make that change to it. If I put the negative out in front, okay, that's the key right there, where the negative is at. If the negative is in front of the function, if it's a parabola, think like y equals x squared, and when I put a negative in front of the x squared, it takes that parabola and moves it upside down. It reflects it over the x-axis. So it's going to just be moving or opening in a different direction than what it started with originally. Okay? So the negative goes in front of the function, whatever that might be. The other type of reflection, and this one's probably not as common, is a reflection in the y-axis. We haven't seen this one quite as often. Once again, if f of x is my original function, then here we're going to say y equals f of negative x. Here the negative goes on the inside of the function. And I'm going to show you an example here in just a second so you can kind of understand what's going on. But where the negative's at is the key. Those are the only 2 kinds of reflections that we're going to focus on. And probably the x-axis is going to be the one that we're going to see the most. So if I gave you y equals x squared, then y equals negative x squared is going to take the graph and flip it upside down. So this would be the graph of f of x equals negative x squared. It's my original x squared function, but it's just going to be moving it down. Now, as we start to go through the lesson today, then we're going to keep adding in the things that we've already talked about, right? So we're going to still see things that, what if I had something like this, and I ask you to apply or tell me all the changes that are happening within this function. Well, there's 3 different things. To go from the original function to what we've got now, okay? Earlier we talked about this is going to move it right 3, this is going to move it up 4, and this is going to reflect the x-axis, okay? And so we would want to say something like that. Right 3, up 4, and reflect the x-axis. You've probably in the past used the word flip over the x-axis. I'm okay with that. I mean, it's telling you what you're doing. Okay, reflect is probably the more mathematical word that you're going to see. But if you're just describing it to me in your own words, then I'm totally fine with saying flip. Kind of like slide versus shift. Okay, it's all kind of the same thing, just a little bit different terminology. But if flip makes more sense to you, then that's totally okay. And so just a real quick sketch of this graph. This is where my new vertex is going to be, okay? It was originally a 0, 0 to start with for the x squared. It's going to move right 3, it's going to move up 4, and then it's going to flip upside down. Now, when I say it's going to reflect over the x-axis, then it doesn't mean it's going to be below the x-axis because our original movement has changed, right? It's not a 0, 0 anymore. So it's not like this one here where it's got to stay below the x-axis because of the shift that's taking place. So keep that in mind too, that it's going to look a little bit different. But it's taking all of those into account, right? All the different changes that are happening. Let's take a look at one with the y-axis, where it's going to reflect the y-axis. Let's say we used x cubed. That's a good one to use. If y equals x cubed, and I do y equals negative x cubed, here we're putting the negative on the inside, okay? And so we're going to reflect the y-axis. Let's take a look at what that would look like. The original graph. Okay, the last one we're going to talk about and there's two different ones of this. There's vertical stretch and shrink, and then in just a second we're going to talk about horizontal stretch and shrink, okay? And they are a little bit different based on where the number is at, so the wording that we use associated with them is going to be a little bit different. And this one is kind of different to think about, but I'll try to make it as easy as possible to kind of help you out here. So let's start with f of x equals the original, whatever that function is. If I do y equals a times f of x, that a value is always going to be in the same place. It's always going to be out in the front of the function. But what that number is going to change what's happening. Okay, so if that a value is bigger than 1, okay? The reason I put the absolute value in there is because we don't want to pay attention to negatives. Negative is what we just talked about. The negative is going to make it flip. So we don't want to worry about the negative here. So we're only looking at the number itself. So they use the word, or use the absolute value symbol, because we only want to look at the positive value. Don't worry about the negative. So essentially, if that a value is bigger than 1, then we would say that it's going to be a vertical stretch. And what's going to happen is that graph, imagine a parabola, it's going to stretch it, and it's going to become really skinny, okay? And we'll look at some examples. But if the number is bigger than 1, the bigger the number, the more it's going to stretch, the skinnier it will be. If I put in like a 10 in front of it, it's going to make it a really, really skinny U. Okay? As opposed to if that a value is between 0 and 1. So here we're looking at numbers like a half, a fourth, a third, any fraction or decimal between 0 and 1. We call this a vertical shrink. Okay, and we're talking vertical here. Okay, so vertical, if I stretch something vertically, okay, then I'm going to take it, I think of it like Play-Doh or something that you can stretch. And I can stretch it up and down, right? It gets really skinny as I stretch it. If I shrink something, then it's going to be like I'm smashing it, right? So I can take this big thing of Play-Doh, if I had some Play-Doh, and I can smash it, and it's going to make it widen out, right? And so it's going to get really fat as I smash it. And the more that I smash it, the wider that it gets. And so the same thing here will hold true, okay? The bigger or the smaller the number is going to change how much it shrinks. but when I shrink, it's going to make it widen, okay? So that's what we call vertical and stretch or shrink. We can also then do a horizontal stretch or shrink. Okay, and once again, f of x is my original. This time, we're going to put the c value on the inside, okay? Here I used the a value, and the a value is out in front. Here the c value is the new number that we're adding to the function, and it's going to be on the inside of the function. So where that number is at tells us what type of stretch or shrink is taking place. If the absolute value of c is bigger than 1, then it will take on the same thing as that, okay? But we would call this a horizontal shrink. Okay, the wording is different, okay? Because think about it this way, and here's where it gets a little bit tricky, but visually, I think this makes the most sense, okay? If I were to take a piece of gum or Play-Doh or whatever you want to talk about stretching, right? Something that's stretchy. And vertically, I would go this way, right? But if I come in from the side and I smash it horizontally, then what's going to happen to it? Then it's going to get skinny again, right? So it has the same effect. So a horizontal smash is the same as a vertical stretch, okay? And that smash is what they were referring to as the shrink. And then if that c value is between 0 and 1, then that would be a horizontal stretch. And that is going to be the same as a vertical shrink. Okay, those two wordings are the same. But depending on the word or where the number is, if the number's on the inside, it's a horizontal stretch or shrink. If the number's on the front of the function, then it's going to be a vertical stretch or shrink. So we just have to, where that number is at tells us what type of stretch or shrink we have, horizontal versus vertical. Okay, I'm going to show you an example that I think will help you to kind of understand what's really going on here. Let's think about a function. Y equals the absolute value of x. Okay, absolute value function makes a v. We've seen it a couple of times throughout the first couple of chapters. If I put a 4 in front of the function, and I put a 4 on the inside of the function. Okay, let's talk about what happens here. Let's look at the graph. These is you can use your graph to really help you out, right? You can use your calculator to plug it in and kind of help you describe what's going on. And I'm totally okay with that. I've told you since day one that your calculator is a great tool to be able to use here and help you to describe some of these things. So like if you're on your test on Thursday and you're trying to help describe what's going on in the graph, plug it into the calculator, use that graph to help you describe what's going on. But I always like to go back to the original. They may not always put the original function, but you're describing what the change is from the original to the new one. That's the big thing, okay? So before I move on from this, we said that this was a vertical stretch of 4 because the 4 is out in front, whereas this one is a horizontal shrink by 4. Okay, different wording, the graph still looked the same. All right, last thing I'm going to go over here. If I gave you an ordered pair, and I said f of x minus 3. I want you to tell me where this point would go, where would it be if I applied this movement to it, okay? So sometimes we'll do it to an entire function. Here we're just doing it to a single point, okay? Doesn't change. It's the same idea. So the first thing we want to identify is what kind of movement is going to happen here. Where would this point go? What's this saying? What'd you say? Right 3. Okay, so that's what we want to think about here. This is going to move right 3. Okay, when I move left or right, what value changes? What value moves left and right? X or Y? X, right? So the X value is going to be the one that changes. We're going to take our X value and we're going to move it right 3. Okay, and so in this case, we would say my new point would be at 15.3. We're going to take that point and we're going to move it to the right 3 units. The Y value does not change. Okay. If I did one like this, here the minus 4 is after or at the end of the function. So this is telling us it's going to go down 4. If I move up and down, then the only thing that's being changed here is the Y value, because the Y values are the values that move up and down. My original Y value was 3. I'm going back to the original. I'm not starting back here again. I'm starting that back at the original. If I move this point down 4, the X value will not change. My 3 is going to go down 4, which would put us at negative 1. So only one of those, there's only one change taking place, so only one value is going to change, okay? I could put in 2 changes here, and so then maybe X and Y would both change. The last one I'm going to do here with you is Y equals 3 times f of x. Okay, 12.3 is on the original function, okay? And I never really said that, but this point would be on the original function. And so we want to figure out where it would end up, okay? Well, the 3, here's the easiest way to do this problem. F of x is really a fancy way of saying y, right? Way back from chapter 1 when we talked about function notation and we said f of x really replaces the y. So this is really saying 3 times y. F of x is y. So we're going to take the y value, which is 3, and we're going to multiply it by 3, which is going to stretch it by 3. And you don't necessarily have to say that it's stretching by 3, but my new point here would be 12.9. We're going to take the y value, and we're multiplying it by 3. Okay. So there's some different variations of those that you can see. Most of the time I'll probably just give you ones that are like addition, subtraction, but you might see some of the vertical and horizontal stretch ones in there as well. But the biggest ones are just moving it left, right, up or down. Okay. I'm going to do number 10 with you. Number 10 is a little bit tricky. It's one of the problems from your homework. So you can put it at the very beginning of your homework assignment if you want to. and it'll be done. Okay, as we went through the lesson today, I tried to show you some of the different functions that you're going to see. We did some absolute value, we did some quadratic, we did some cubic, we did a square root at one point. What type of function is this? Linear, right? It's just going to be a line, okay? And that's one of our functions, and that's probably the one we've dealt with the most, okay? But how do I describe my changes based on what's going on here, okay? So the original function is y equals x. Has a y-intercept of 0 and a slope of 1. That's my original function. Okay, this one's obviously in slope-intercept form. And so two things are happening here. We have to identify and identify two things that are going on. Okay, what does the plus 1 do? Up 1. Okay, so this is going to move it up 1. Okay, and then the 2 is going to do what to it? Yep, it's going to be a vertical stretch by 2. And the reason I do this one with you is because I think, especially for linear equations, it's kind of weird. They're asking me to then do a graph of this function. So on the first 4 problems, 5, 10, 15, and 20, you're going to describe the changes and you're going to graph a sketch. It's only asking you to sketch the new one. I like to sketch the original one as well. You don't necessarily have to, but I think it helps to kind of see the changes taking place. So this would be my original. Y-intercept of 0, slope of 1. And then my new one is going to move up 1. And then we know that when we have a slope of 2, it's going to make it rise a little bit quicker. You could also go down 2 and left 1 if you wanted to, but the different slope, it's rising faster, right? It's got a little bit more incline to it, so it's making it stretch or rise a little bit quicker. And so that would be what your graph would look like. If you don't want to put this one, you don't have to, but I kind of like adding the original in there sometimes just to show the difference of what's going on. I don't think I drew the original on my answers, but that's definitely something you can do if it helps you visually, okay? All right, I'll let you guys work.
Mr. Rubin,
Yeah.
can I get the study guide for like the